Hello R peeps, this is a BinMat tutorial for the R package called BinMat that I created to help with the analysis of fragment data such as that obtained from ISSRs and AFLPs. So, to start with, it is assumed that the data that you put into BinMat is already a binary matrix, that it has been processed by a program such as GeneMarker and or Geno. So in other words, the electropherograms that are received from a sequencing facility have been input into these programs, and using the various filters and settings have been transformed into presence or absence data. So this is what is input into BinMat, and then one of the most helpful features of this package is that it can automatically consolidate replicate pairs. So for example, if you have one particular sample that you have replicated in a PCR machine, and now you have rep 1 and rep 2, you want a consensus output. So let's say at the first locus both reps had or showed the absence of a peak. That output is 0. If one rep had a presence, reported a presence at this locus but rep 2 didn't, that would be output as a question mark because that is ambiguous. And then obviously if both showed the presence of a peak as a 1, that will be output as a 1. And so that's the general pattern, and so you want to have this one output that represents 2 replicates. And once the program has done this, it then creates a distance matrix using the Jacon's index. This is an important one because it doesn't take the shared absence of a band as being biologically meaningful. So in other words, it discards all of that and only really looks at presence data. So once you have this distance matrix, that can be then used to create hierarchical clustering trees or NMDS plots, so that they can show you, what patterns you have in your data and possible trends. And then there's also the functionality of removing some samples that maybe fall below a certain peak threshold that you designate. So I'll go through the various functions and how this can be applied. There are 11 functions in this package, and we will go through them now. So first off, you go to install, and BinMat is on the CRAN repository. So we'll just start typing in BinMat, select it here, and install. That should be fairly quick. And then you will type library BinMat so that you can start accessing various functions. So I have some made up data here. So for example, let's say you've got this output from, you've processed your electropherograms in GeneMarker, and then you further filtered them in raw Geno. Now you've got this output. So your first row needs to have a heading for sample, and these X's you see here are just arbitrary names for locus positions. It doesn't actually matter what this is as long as there's a row here. And then these will be your sample names, and then this is your actual matrix. So in this case, A1 and A2 are replicates for sample A, and B1 and B2 for sample B. And what's really important is that you have to have these replicate pairs together like this. So you can't have A1 here and A2 down here. They have to be together because the program automatically takes every pair, and so whatever's underneath it, that is what it's working with. It doesn't know that this is supposed to both be reps for sample A. It just has to be in this exact format. So what we're going to do is read this one into BinMat. So the usual way of reading in a CSV file is using this read.csv function and then providing it with the address of that file. But what I found to be just easier is using the same thing, but then instead of putting in the file address, you can use this file.choose command, and if you run this, you'll see it opening up a window where you can actually select the file, and then it just automatically feeds in all the information it needs. So I've read that in, and we can have a quick look at what this data looks like. So here it is. So the first function is a quick one. It's check.data, and you provide it with the name of the data. So I've called it ISSR_reps. So what this does is it just searches through the matrix and makes sure that there's nothing other than ones and zeros present. I just thought it was quite cool. I mean, maybe you've got a foreign character that crept in somewhere. So if you run this code, it will say, okay, none found. If it did, it would give you the row and column position of where that intruder is. So the next function is called peaks.original, and again, it just needs the name of your data. This just gives you summary information about the average number of peaks in that data set and its standard deviation, and the max and minimum number of peaks are detected throughout those samples, and it just confirms the number of loci. So you'll see there are 14, and yeah, this is just quite nice to report. So now an important one, this is what I was speaking about when your replicates are consolidated. So have a look at this original again. So there are 8 samples in total, so once we've consolidated it, we are expecting a matrix with 4 rows. So for example, you see A1 and A2. So here we're expecting sample A to have an output at locus 1 or 0. The next locus would be a question mark because there's a 0 and a 1. This would be a 1, a 1, a 1, a 0, 1, 0, question mark, etc. So I'm creating an object called cons for consolidated, and the function name is consolidate, and I feed in the name of that data set. So you run that line, and then we can actually check what this looks like. So have a look, we've got A1 and A2 combined, and this is the consensus output for those two. You can see the second position here should be a question mark. You can check this if you want, but it does the job. What you can now do is you can, just as we looked for the number of peaks in the original set when all the replicates were still present, we can do the same now for the consolidated matrix. So that's peaks.consolidated, and the argument that you feed in here is your consolidated matrix. So we can run that, and this is the new summary output for the consolidated one. And then of course we can start looking at the error rates. That's just the function's errors, and again you feed it in your consolidated matrix. This will give you your average Euclidean error and its standard deviation, and the Jaccard error and its standard deviation. Now the Jaccard error will always present an error rate higher than the Euclidean error rate, because this one doesn't take, as I said earlier, the shared absence of a band into account. It just discards that, whereas the Euclidean error does take that into account. So I would imagine that it's better to just report both. I think it's just probably good practice. What you can then do is, if you want to, you can filter this consolidated matrix. So have a look at it again here. let's say you want to say, well, okay, I want to remove a row where there are peaks that are less than a certain number. So let's say I say, okay, peak.remove is the name of the function, and I feed it in this consolidated matrix, and the second argument is the threshold. So this is saying remove all the samples that have peaks less than 5. So if I run that, it'll tell you here one sample was removed, and this was sample C. And then if I look, this is, I called it rem for removed. This new filtered matrix is now stored under this name, and if I look at this, you'll see that it is A, B, and D. So C has been removed. So the cons matrix is still the same, it still contains everything, but the removed one now has that one row removed, and it's just quite a nifty thing that you can do if you want to. The final part of this little section is now creating a clustering tree based on this consolidated matrix, and the function is upgma, and again you just feed in your consolidated matrix, and it does include replicates, like bootstrap kind of replications. You'll see if you start typing the function, you'll see what kind of arguments you can play around with. So here BTS is bootstraps, and it's just set to 10 by default, but ideally you would set that to 1000. And then you can also play around with the label sizes. These are all just defaults. I'll explain what this from file means a little later. It's set to false now because you haven't, this consolidated matrix hasn't been uploaded as a separate thing. It's been processed right from the beginning, from that very first file. So let's just use the normal default settings for now. So you would run this, and then here you'll see the output. So you'll see here how your samples have clustered. Let's say you want to run this. This is, the cons is now all the samples, but let's say you wanted to do it with the set that has had that sample C removed. You would just run it the same. Here you go. See, it's just minus C. And then you'll see here, you'd look at the green value, that's the bootstrap value. Yeah, that's pretty much, and this is, yes, this is a percentage. So that's the first part, and then just for interest's sake, let's say you now want to take this consolidated matrix, let's just get it up here. Let's say you want to write this to Excel, right? You want to save it as a file. The command to do that is write.csv. The first argument is the name of the data set that you want, and the second argument is the address where you want to save it to. So in my case, I'm just saving it to the desktop, and then this last slash is followed by the name. You can name it anything you want as long as you put the .csv extension there. And if you run this, if I now go and look at my desktop, you'll see here consolidate. There's the file. So that is pretty much the first part. Now I've run through most of the functions. Now the second part of this package now looks at you having grouped data. So for example, let's say you've got a data set like this. You've got your samples that have now already been consolidated. They're in their final form. You've got your matrix exactly. So this, the file that I wrote just now, this consolidated, exactly this, but there's now a column in column 2 for group. So you manually add this. So let's say I now open this consolidated file, and I now need to add grouping information. I mean, that's how you would color code your NMDS plot by group. So let's just give it a moment. Yes, okay, so here it is. So what you would do now is you would just insert a column. This is column right. You can call it anything you want, just call it group. And then, depending obviously on where your samples were collected, let's say this was Asia, this was Africa, this one was Asia, you get the point. So you would fill this out and save this. So this is basically what I'm talking about now. This is what I've got here. This is just another made up data set. So what you do now, again, you read this file in, again using this file.choose, and this is my file that I showed you now. And if I want to view it, have a look, again 14 loci and different sample names and grouping information. So there's a function called group.names, and you again input the data, the name of the data set, and it will just quickly tell you, okay, you've got Africa, Australia and Europe as groups. Then you can, as before, you can create a UPGMA clustering tree. So this time you send in the name, you give it the name of the dataset, and then you say from file equals t equals true, because you've just read this in. It hasn't been, you haven't just consolidated this in the package and carried it through. This is now read in as a separate thing. So that's the only reason why that's from file. So you run that, and here you go. It's giving you, remember the sample names were just letters, so that's why it appears like this. And as before, you can give it other arguments. You can change the size and of course increase the bootstrap replications. So now probably the best part really, I mean, NMDS plots and any kind of ordination plot is really great because it allows you to see how your data groups and what's more similar to what. So first off, you need to run what's called a scree plot, and what you do here is you just type in the function scree and you put in your ISSR, the name of this file. You'll see it brings up a plot like this, and a scree plot basically shows you what optimal number of dimensions you should be using for your NMDS plot in order to minimize the stress value. If you want more info about this, there's quite a lot you can research, but what I do recommend is if you look at, you go to your packages in the BinMat package, there is all the functions are listed here with a brief description, and if you do want more, you just click on it here, and there's a brief summary and all the information you need for the arguments. But from the reading I have done, it seems as though a stress value less than 0.15 is acceptable. So in this case, number of dimensions, any 2, 3 or 4 is fine, but usually the less the better, so we'll go with 2. So what you then do is you can create a shepherd plot, and well, you'll see this basically shows a line of best fit through your points, and you want the R squared, I mean the higher the R squared value is, the better the data fits. So this shows you, okay, it's pretty alright. So what I forgot to mention was when you are creating your scree plot, one of the arguments that you can adjust is the dimensions, and that's what I mentioned earlier. You're looking for what the optimal number should be. So it's set to 4 by default, which is why you'll see it's only plotted 4 here. But then, so you'll decide, okay, number of dimensions, I'm going to go with 2, let's say. So you can play around with that in the shepherd function. So for instance, if you look here, the k value is basically the number of dimensions. So you're plotting it for k is equal to 2. So you can, that's the default. So when you look at this plot, that is assuming that you're going to plot for 2 dimensions, and because it's quite a reasonable fit, you can stick with that. What you then need to do is you want to plot the NNDS. So if you have a look at this NNDS function, it requires colors and shape information. So what you need to do prior to actually plotting this is you need to create 2 objects. I've just called it CLRS for colors and SHPS for shapes. You can call it whatever you want. And because I know that I've only got the 2 groups, did I have more? Oh no, I had more, sorry. I've got 3 groups. That's why this function is quite handy. So then I know I need to designate 3 colors. So I'll say red, blue, and green. So you have to just be aware that this is going to be the exact order. So it's alphabetical. So red will be assigned to Africa, blue will be to Australia, and green will be to Europe. The same will be with shapes. So 16 is just your standard circle, but you can, if you look up PCH options for R, you'll see that there are different values for different shapes, like triangles and squares and whatnot. So I'll just go with all circles for now. So I'll run these, and then my NNDS function, I will pass as a first argument the data set, and then colors, pass it through this object, shapes, give it that object, and then labels, you can say true or false. You'll see if I put, let's go with F for now, it will show up like this. If I say T, it's quite nice because you can actually see what's what. That is the basic rundown. The next thing that I really wanted to emphasize was this whole package is available as a graphical user interface. If you go to the information about the package description file here, you'll see that there is a URL, Shiny Online Server. So if you copy and paste this address, Shiny Apps, and you paste it in your web browser, it will bring up this interface, and all the same functions are available here. It's just all it's just all buttons instead of coding in R. So there's an option to upload, you can check for unwanted values, you consolidate, you download, and then the tabs here are where you can get your summary info, and you can download, you can get your error rates, you can plot your tree, set the bootstrap number. Here's your NMDS plot. Here's the scree and shepherd. Here's your option to filter. When you actually do the NMDS plotter table, well, actually let me show you what happens. You upload your grouping. Did I miss something? Oh, sorry, I have to do it here. Open your file, and a table should pop up. Yes, here, where you can color your your groups, you just select from the drop down menu, and all the colors in R are available, as well as the different point shapes. And again, you can choose your dimensions, and you can also select whether you want sample labels to be shown. You can adjust the point size. So let's say you want Africa to be red, Europe can be blue, and Australia can be green, and we'll stick with them being circles. And I have just added in this different distance method. So binary is the Jacquard index, although you can choose others if you want to play around with it for whatever reason. Let's say we go with the 2 dimensions plot. Here's your plot. You can show sample labels, and you can increase point size. If you do, you drag, and then you just have to click on plot, and then it will just update. And then you can download this as a SVG file that you can further process in something like Inkscape, and edit it in whichever way you like. Again, Scree plot, exactly the same as we saw earlier. You can download this, and you can also get your shepherd plot here. Again, you see it's the same. If I go back here and I start playing around with a number of dimensions, you'll see how it starts to change. If I've changed it to 3, and I go back to this validation, you'll see that it's slightly changed. Remember, it was 0.76 earlier, so it's even better fit, although it does seem that the least number of dimensions is preferable. So this is the basic idea. I can do another separate tutorial on this if need be. What I do recommend is that there is a help file. You can click on this little question mark, and it will bring up all the information about the program, the format that the data needs to be in. It will explain, what each function does, and a little bit about the calculation of the Jacquard and Euclidean error rates, which might be of use. Furthermore, if you do check out the R CRAN website, there's also a brief summary of the package here. And what's really worth looking at is the vignette here. You can have a look. It's also a summary of the package, but what's really cool is that it's a markdown file, and as such there's a worked example down here, and this code actually runs on this browser, so it works for sure. It's using the same example data set as I've been using in this tutorial. So have a quick squiz at this. Here's an example of where I've changed some of the point shapes and such. I think I did that up here somewhere. Anyway, look through it, and yes, email me if there are any questions. My email address is here as well. If you look through this information here, vstendron@gmail.com. And another thing to take note of, sometimes when you use the server and you upload an enormous data set, this Shiny Apps server will time out because it is on a free plan. And to solve that problem, I have made this code available on GitHub. And if you run this line of code, you can run this exact same user interface in your R itself, and then you can upload larger data sets. So all you need to first do is install the Shiny package, again, you just go to packages here, install. If you start typing in Shiny, it's this one. You just install that and you run this line. So have a look. If I run this, it fetches all that code from GitHub, and yeah, it just makes it accessible here. So you get this window popping up, and assuming all the packages are automatically loaded, it's just Shiny that you need. It might take a little while to actually load. Give it some time. Yes. Okay, so it might take a few minutes for this to load, depending on which packages you might already have installed, but it does automatically install everything that it requires. It's only the Shiny package that you need. So here it is. It will appear exactly as you saw earlier on this browser. So that is pretty much the rundown. Again, have a look through all of these functions and check out what the arguments must be. There's usually a little example following that and a description. There are often quite a few things that you can tweak, especially when it comes to plotting the NMDS plot. As you can see here, you can select distance method, dimensions, size, colors, shapes, labels, all of this kind of thing. So if there are any questions, please email me. This video will be available, and I will make sure that this code accompanies it, as well as the links to this CRAN page, the way you can access this vignette, and also this Shiny Apps link. Alright, that is me. Good luck, and yes, let me know if I need to make a follow-up video or if there's anything that wasn't clear, and all the best.